Let's summarize this part then. Many optimization problems do not have direct analytical solutions. And a more broadly applicable strategy is to employ an iterative-based solution, which we're going to call gradient descent. And iterative here means that we're going to apply and update repeatedly to our objective until some criterion is met. So the general approach is going to be that we're going to initialize the weights W to some value. In the case of analytical, we didn't have any initialization, right? It was just, here's a solution based on your data. But in the case of iterative approaches, we always have to start somewhere and iterate from there. And so we're going to initialize the weight values based on some approach. Perhaps we're just going to set all of them to 0. That sometimes works. And then we're going to repeatedly adjust the weight values until we minimize the loss to a point which is satisfactory. And of course, because we hope that every step minimizes the loss for us, we're going to be moving in the direction of steepest descent, whatever that means. Okay, so let's try to build some intuition here. Let's say I have my loss function again, this loss function here, my empirical loss. I'm operating in a 1D space, so I have a 1D space of my W's, which I can change. I can change the value of W, and I can see how the value of the loss would change as a result of my change in W. Now, the main intuition I want you to take away from this is that gradients, the gradients of a function, indicate the direction of change in that function. It tells us which direction does the function change the most. That's what gradients tell us. And so they're well suited to tell us where the maxima and minima of functions lie. How? The way we do it is that we're going to take a step in the direction pointed by the gradient, and then we're going to repeat until the values of W converges. What does all this mean? So let's consider these two questions. Let's say that the gradient of my loss function according to the dimension W is positive. I'm looking at this example first. So what does this mean? This means that I'm somewhere here, right? And my gradient is positive. Now the question that I pose for you is, if I decrease the value of W, how does this affect the value of the loss? Right here, this is Wj. I'm saying if I decrease the value of W, how does my loss change? Guru, you're on mute.
It decreases.
Right, so we can see that going from one point to another point, the value of the loss goes down. Let's look at the converse of this, and then we can take questions if anything's still unclear. Let's say that the value of the gradient is negative. What's an example of that? This point here. This point in green has a negative value of the gradient. Now my question for you is, if I increase the value of Wj, how does the loss change?
Still decreases.
It once again decreases. So what do I do with this information? What was our objective? Our objective was to decrease the loss. And at every point, I've measured the gradient of the loss with respect to W. And now intuition in this figure is telling us that if the gradient is positive, then decreasing it decreases the loss. Tells us if the gradient is negative, then increasing it decreases the loss. So maybe let's put both of these ideas together and say that, right, so the sign of W will determine the direction in which our loss decreases the most. So if I want to put these ideas together, maybe a reasonable update rule for my loss is the one at the top of the page here. I'm going to say that at iteration t+1 of my iterative optimization problem, I'm going to take the previous value of Wj at iteration t, and I'm going to subtract the value of the gradient from it. If the gradient is positive, then of course I'm going to be moving towards the part where loss goes down. If the gradient is negative, I'm going to be moving towards the part where the loss again goes down. So What does that look like iteratively? I'm at this point here, gradient is negative, take a step towards the next point. Again, the gradient is negative, take another step towards the next point. Repeat until I get to a critical point. If not questions, can someone help me summarize gradient descent?
I have a question.
Mm-hmm.
Can you say the first line again? A reasonable update. Why it is equal this?
Sorry, could you say that again?
About reasonable update. Why it is equal this equation?
Mm-hmm. Okay, so let's go back to the previous slide. What are we saying on this slide? We're saying that the iterative solution that we're studying says this. Says I'm going to start with some value of w, right? And this value of w could be 0, could be 300, it could be 20.5, whatever, some value of w. That value of w with it will determine some value of loss that I'm trying to minimize, right? Because the loss function is dependent on the values of w. Now, what I'm claiming here, or what the gradient descent approach wants you to take into consideration, is that if you look at the gradient of the loss that we're trying to minimize, if you look at the gradient of the loss function with respect to that value of w, 20.5, whatever it was, then the gradient will point in the direction in which the loss decreases the most. That's the overall intuition. And now we're seeing two cases of this. If the gradient is positive, like in the case of some wj here, then we just need to move in the opposite direction. If the gradient is negative, like this point here, then again, we need to move in the opposite direction. So the value of j at time t needs to be subtracted, moving in the opposite direction, by the loss, the derivative of the loss with respect to wj. And that is what I will set to be the value of my weight vector at the next iteration. And then I just repeat. Now there's something missing from this figure, and that is on the next slide, there's an alpha here. And the alpha is what we call the learning rate or the step size. The reason there's an alpha is because I could take a million very small steps, or I could take one very large step, or somewhere in between. And that determines, how fast or how slow or how well I move towards the optimal solution.
Thank you.
Mm-hmm. Okay, so right, the larger the alpha is, the faster w changes, and values of alpha are typically rather small. They're like 1 over 100 or 1 over 10,000, something like that. Now, does anyone see any problems with this approach? Yes, Safida.
So as we said last session, so alpha is a hyperparameter, and we can't say anything about hyperparameters. I mean that if we choose alpha smaller, so we will hit the target slowly. But if we choose the alpha bigger, we may not hit the target. And we
may not hit the target. Right. So in this case, if I choose a very large alpha, I might see something that goes like this, and then goes like this, and then goes like that, and then goes like that, and never will it actually hit the minimum point here. Right. So that's the risk of choosing too large of an alpha. Are there any other risks?
If we take alpha large, then we miss the local minima point. And if we take alpha small, then we take many steps to converge the model.
Okay.
So I think adaptive learning rate is most suitable in this case.
Okay, right. So you could be very clever and not choose a fixed learning rate, and that gets into its own can of worms and difficulties. But there was something in your answer that is actually perhaps a different problem itself. What type of minima did you say it would find?
Actually, we want to find a point where loss function is minimum.
Okay.
So we need that W's where loss function is minimum. So
Okay. Absolutely. So let me just expand this picture a bit for you and say that actually this is not the whole picture. My loss function looks something like this.
okay.
This is called a local minima, and this point here is called a global minima. What's
But
the difference between local and global minima?
sorry, will you repeat?
Just what is the intuitive difference between local and global minima?
Global minima is the point in your region where your loss is actually minimum. But in local minimum point, you get the feeling of it is the actual local minima, but there is
Right.
just another point where global local minima exist.
So global minima means over the entire domain of the
Yeah.
function, this is the absolute lowest point. Whereas local minima just means that within a neighborhood, it's the lowest point. So let's say that I've started off at this point here. Remember, Paisa, we said we could start off with, random points for our W, 20.5 or whatever number. I've started here. I'm following the instructions very carefully. I'm computing the gradients. I've set a reasonable alpha. I'm taking a step. I'm taking a step. I'm taking a step. And I might end up here, and then I'll go back a bit. And ultimately, I just stop there. But actually, there is a point down here which has a better value of the loss for some value of my W. And so one of the risks of doing gradient descent is what? Is not only do we need to select hyperparameters like Sepida is saying, including the learning rate, as well as the initialization point, but at the end of the day, depending on the form of the loss function, we might end up in local optima rather than global optima. Yes.
But mean squared error is a convex function.
Okay, good point. You're right. Absolutely. I'm talking about general gradient descent, but Mujtaba is very right in that mean squared error, when applied over the model class of a linear model class, is actually a convex loss. And you all know from the self-assessment quiz that convex losses mean that any local minima is actually the global minima because there's only one minimum. Or there might be more than one minima. Like in this case, we have infinitely many local minima, but all of them are the global minima. Absolutely. Yes. So general gradient descent has the issue of selecting learning rate, has the issue of selecting initialization, and being sensitive to it. That's why you see, at least for the case of small scale models, you might want to restart your initialization several times, right, to see whether you get a better result overall. Yes, Guru.
So if I assume that the error function in higher dimensions might be some kind of might even have a saddle point, right?
Mm-hmm. Yes. So we're talking about here the intuition for a single dimensional input, and we're trying to do gradient descent. In high dimension loss landscapes, anything happens. We have saddle points, we have valleys, we have plateaus, and valleys mean like a very big dip. So the loss might look something like this, and depending on our learning rate, we might just completely jump over that. A plateau might mean something like this. Just you might have a small learning rate to overcome something like a valley, but then you'll take infinitely many time to cross a plateau, or you might have a saddle point, and there's many issues with this. But it's an iterative approach. It applies almost to any situation where you have a loss function, which is what, Sepide? What do we need our loss function to be? Shima mentioned this. We want it to be differentiable, right? Why do we want it to be differentiable? Because we're taking gradients, and gradients assume that we have a differentiable function, at least at that point which the gradient is being taken. All right, so any problems with this? We might not find the global optima, and this is sensitive to W naught, our initialization, as well as our learning rate. Yes, Safida.
So we don't use gradient descent for non-convex functions.
That's a good question. Actually, we do. In fact, there are many, when we study neural networks, it's really not expected for the loss of a complicated neural network to be convex, but we really don't have any choice because we don't have closed form solutions for the global optima. So really, at best, we can only do local optima. And there, it's recommended to not only just stick with the result of one optimization process, but just repeat it multiple times, change the random seed, right? See which one gives you best. And once you find the best, by the way, on random seeds are, something that we set in our code to say that whatever random process that I have, I want it to be repetitive in the same way, right? And one of the things that we randomly select based on the seed that we have is the point of initialization. And so if we found a good setting, it's very important to keep track of what the seed is.
Mhm.
That's highly recommended in many machine learning experiments.
That makes sense.
Okay, excellent. So to summarize the gradient descent intuition, then, of course, gradient descent gets its name from the gradient. In this case, it's a vector over partial gradients of the loss function over all the dimensions that I have. We looked at the case of a scalar form of update rule, but we need not stick with scalar. We can take the vectorized version, and that's what we do really in higher dimensions. And it turns out that if you want to write out the update rule for the particular loss and model that we're studying today, it looks something like this. Excellent. So to summarize gradient descent, it's more broadly applicable to models that don't have closed form analytical solutions. It's easier to implement the direct solutions. And also, it's more efficient than a direct analytical solution, especially for the higher dimensional spaces. We saw the closed form expression for least squares linear regression is something like this. We know that the inversion, if at all possible, scales cubically. It turns out that every step of gradient descent only costs us O of ND. So depending on how many steps you need to take, if your dimensions are high, then probably there's going to be a huge difference between the closed form global optima solution and the local optima solution with gradient descent.